Hello, my dear friends. So today is the fifth lecture in the EMFT Electromagnetic Field Theory, code KE301. So today we are going to start the gradient of a scalar, divergence, and the Stokes theorem. Okay. So first thing is the gradient. What exactly gradient is? Gradient is nothing but gradient can be will be of your scalar quantity only, or the scalar field. First thing, this is very important. Second thing is about the gradient. The result or output of the gradient is the vector quantity. It means it will give the magnitude and the directions. Okay. So what exactly meaning of that one is? The gradient means that when we are moving in the scalar field, right, in like in the potential, right, or temperature or pressure. So in this, when we are moving from one point to another point, so in that case the difference of the field measurement is called the gradient. If we want to move from, just like if for this region the potential is V1 and above that at a difference of delta V the potential is V2 and above that the potential V3. Okay. So in this case when we are moving from P1 to P2, so in this case then we have the maximum space rate of change or increase in the potential is nothing but the gradient. Okay. So here if at this point P1, when we have at this point, so at this point P1 when we have the potential V1 and we are moving into the next delta V difference of the potential into that particular scalar field, that is a P2. So from P1 to P2 when we have the maximum space rate of change of increase of V, then we call the gradient of that quantity, and the magnitude is there and the direction of that field is also be present. So same thing happen from we are moving from P2 to P3 as well. Okay. So we will take the derivation of this, how we can get the gradient of these things. But important point is maximum space rate of increase of potential. So in that the delta V, when we are talking about this del V, right? So I will take the derivation for this. We will go for the derivation part. So in this, that first is a del dV, that is a total differentiation of the potential. That is equal to del V upon del X into del dx plus del V upon del Y into dy plus del V upon del Z into dz. So we can bifurcate this portion. So we can write this one as in this way, that del V upon del X Ax plus del V upon del Y Ay plus del V upon del Z Az, and dx Ax, dy Ay, dz Az. So when you multiply these two with the dot product, then we will get the same result. Okay. So we are starting from here. So for our convenience, what we are writing, this one we are writing as the G, because we are taking the gradient part, and this one is nothing but this is the dl, displacement. So dl is the displacement. So here itself this is the dl, displacement of the potential from point P1 to point P2. So now we can write this one dl dv. So we can write this dv as the G into dl. Okay. So in this we can also write G dot dl is equal to G cos theta into dl, right? And we can take downward in denominator. So dv upon dl. So you can this dl here. So dv upon dl is equal to G cos theta, right? So this dv upon dl is the rate. This is not the maximum rate. Right now this is the space rate, right? So now this is a space rate. Now we want the maximum space rate of increase of V. So for that one maximum part, cos theta must be 1. So cos theta must be 1 when it is 1, when theta is 0. So when theta is 0, that is the dl is the, in this case dl is in the field will become in the direction of G will be dv upon dl in maximum is equal to, we can write it as a dv upon dn into is equal to G. In this case G is what the gradient value. So in this case we can see when we are moving from point P1 to P2, right, and angle of this one is this angle is 0. It means when we are moving from P1 to P2, then we are getting the maximum space rate of increase of potential. If we are moving from this P1 to here, P1 dash, so this is not the maximum space rate, right? So we want a maximum space rate. In that, when we will get it, when we have G and DL dot product, that is equal to G into DL only, when the theta is 0. I hope this point is clear to all of you. So in this case, in this way we can find that d upon dv upon dl is maximum, dv is equal to dv upon dn. So this is a directional derivative. So this is nothing but the directional derivative. Okay. So in this case we can say directional derivative or the normal derivative. So G is nothing, G has its own magnitude and the direction as those of the maximum rate of increase of V. Okay. So in the Cartesian coordinate, we can write this one as the gradient of V is equal to del V upon del x ax plus del V upon del y ay plus del V upon del z az. So in this way we can define the gradient, and gradient is for only for the scalar quantity. This thing must be keep in mind. When it is for the scalar quantity, and the result of the gradient is nothing but the vector quantity which has the magnitude and the direction. Then we have next is the divergence, divergence of a vector. For that divergence, simply we say divergence is nothing but when we have any isolated positive charge like this. When we have the isolated positive charge, so in this case, right, so this positive charge will emanate the energy. So emanate the electric field. So this electric field is nothing but in this direction, outward of this field, outward of this charge. If this is a positive charge, if it is a negative charge, in that case electric field will be sink into that particular point. So in this way we can say, for when we are taking the divergence of any vector, so it means we will say that we are talking about that particular point at which we want to calculate the divergence. This point can be act as a source or sink. So definition for this one is okay. So before definition, we must see this diagram. It shows the illustration of the point, illustration of divergence at which is concise at the point P when it is a positive charge. So in this case the electric field will emanate outside from this, or this point will be act as a source. When we have this P point, when it is a negative charge, so in this case the charges electric field will be sink into this point, and when there is no diversion and this P point is not a source, not a sink, in this case the same flux line which is going in, the same flux line will come out from there. Okay. So in this case this is the positive divergence, this is the case of the negative divergence, and this is the case of the no divergence. There is no divergence. Okay. In simple fashion we can also say, when we have the input, when the input is suppose okay, so in this case when we have input, just for example, if we have any input that is n and this is the output that is m. Okay. So first case, when we have n is less than m. Okay. If the input lines are less than the output lines, so in this case what will happen? So in this case, when this is lesser than this one is outside, so it means this value is more. When this value is more, in this case, when we in this is the case of the positive divergence. Second, when we have n is greater than m. When n is greater than m, it means the maximum more number of flux lines going in and less numbers for flux lines going out. It means the input is more. So this is the case of the negative divergence. Third one, when we have n is equal to m. So what it shows, when the number of input lines, that is like this one, and the number of output lines, that is that one. So you can say this is the n and this is the m, just for example. So in this case there is no divergence. Okay. So this point is clear, must be clear to all of you. In mathematical portion we can represent that the divergence of any vector at a point P is the outward flux per unit volume as the volume shrinks about point P. So it shows simply that this is the volume, and or in this way also this is nothing but this is the volume, and what we are talking about, that volume is shrinks to point P. So this is a point P. So in this case we can say this is representing like this. So in that, divergence of A is equal to del dot A, and that is equivalent to limit delta V tends to 0. It means the volume shrinks to unity, and it shows that A dot ds closed surface divided by del V when del V del 2 tends to 0. So this is nothing but this is the this is the flux lines. These are flux. Okay. These are when the vector A is passing through the closed surface. Closed surface means the volume, right? Because this is the circle, it shows that, and ds, it shows that this is the volume, and A dot ds, this is the flux lines from the closed surface or the given volume. So it shows the divergence of any vector. So when we talk about the divergence theorem, so what is the divergence theorem? So divergence theorem, it states that the total flux lines, outward flux of a vector field A through a closed surface S is the same as the volume integral of the divergence of that vector A, right? So it means when we have A dot ds, that is a closed surface, this is total flux lines which is going out from the passing through the surface, passing through the closed surface S. Okay, so A is the vector field which is passing through the closed surface S, is equivalent to the volume integral of the divergence of that vector A. Okay, so this is the divergence theorem. So simply we can say that this divergence theorem relate the closed surface with the volume. So obviously when we have the one line, right, and when we are closing this line, this is the open surface, or the open surface of when we are covered that arc with some surfaces, and we are closing that, then this closed surface will become the volume. Okay, it is representing like that. So when we talk about the proof of the divergence theorem, so for that proof we will take the one volume and we will take the small sections of that volume. So this is our volume S, and we are taking the small volumes in that. So this is nothing but this is like that. Like this is not this, all are the volumes, small section volumes. What we are doing, we are simply dividing this complete whole like cylinder kind of things or any solid thing, and we are taking the small sections of that volume, right? So this is, we can say this is nothing but Vk, right? Vk is the kth volume, right? If this is the volume number 1, 2, 3 like that, then we are taking, just for example, we are taking the kth volume. So in this case, when we are taking the left hand side, we are taking from here, we are taking the left hand side, A dot ds. So this is what? This is the complete vector which is passing through this volume. So we can see here, if we have any vector like this, this is the vector A, and this vector A is passing through this complete volume, right? And this complete volume is divided into the small chunks of the volumes. So it means when we sum up all these chunks of the volume, then it will create the complete this volume. So this is equivalent to A dot ds. This Sk is the kth surface, and we are adding all these surfaces, closed surfaces, that is k may be the kth surface. So k may be 1, 2, 3 up to the complete volume of this one, right? So we can we are dividing this delta v tends delta vk, and we multiplying and divide with this to that one, right? So in this way, I think this point is clear to all of you. What we have done, we are taking the left hand side. This is nothing but the vector A passing, or the flux A passing through the closed surface S. Okay, so this is the A dot ds closed outward flux, that is equivalent to the addition of the fluxes which passing through the small chunks of the volumes. So these volumes are SK1, VK1, VK, V1, V2, V3 up to Vk up to Vn and so on up to. So in this case, what we are talking about, we are taking the summation of all these volume, all these fluxes. Then we are dividing and multiply with the delta Vk. So then we will take this one as the volume, limit delta Vk tends to 0. So because what we want, we want the one single point in this, right? Because this is our VK volume. So in this, if I want the one, because as per the definition of divergence, we shrinks this volume to point. So when how we can shrink this point to this point, by taking the delta V tends to 0. Delta V tends to 0. So in this case, this is nothing but the this one, divergence of A. Okay, so we are taking the summation of that. So this is the summation for, we are taking the complete volume. So this will become the del dot A into dV is from here. So that is why we can say that this is the divergence theorem, that is A dot ds is equal to del dot A into dV. Then we can take one of the example. It will be help us to understand more in more efficient way, that if any vector field, just like the vector field was given A, in place of A we are taking the GR. So in this GR is equal to 10 e की power minus 2z rho A rho plus AZ and so on. Determine the flux of G out of the entire surface of the cylinder. So how a cylinder is defined? This cylinder is defined as the rho is equal to 1 and the z is equal to 0 to 1. So it means what is constant? We must be aware what is the points in the cylindrical coordinate system. That was the rho, phi and z. So it means rho is given, that is 1. So this is the hollow cylinder, it shows that. Okay, z is 0 to 1. So the z is 0 to 1, and obviously when we are rotating this with the phi, from by default this value is not given. So it means phi is nothing but 0 to 2 pi. So when it is rotating 0 to 2 pi, then only we will say this cylinder is formed. If the rho is varying from 0 to 1, then it is a solid cylinder. If rho is equal to 1, it means this is the hollow cylinder. I think this point is clear to all of you. So what we want the flux going out from this cylinder. So very simple. So in this case, when we have any vector field like this, and this vector field is nothing but the G. So this is the vector field which is passing through this surface, and we simply want to calculate the total flux. So it means what we required, we have to calculate the flux of that G. So flux will be this one, G dot ds. We have to calculate this, and after that we have to confirm by the divergence theorem. It follows the divergence theorem or not. Okay, I think this question is clear to all of you. G is given. What is our main concern? Our main concern is ds. Now it means if we take closely these surfaces, so it means we have the basic three surfaces. One is this one, second is this one, because this is the hollow cylinder surface, and third one is this one, this is the bottom one. So it means we have to take the surfaces ds as for this surface 1, second and the third. G is already given. So for that one, flux will be G dot ds, right? This is a psi t plus psi b plus delta s. Okay, then we can take this one as first one, top one. So what we are talking about this one. So this flux is nothing but the phi t. This is phi s, this is phi b. So first we will talk about this, that is psi is equal to G dot ds is equal to psi t plus psi b plus psi s. We have to add all these three, and in combined effect we will say this is the outward flux through the surface of the cylinder. Okay, so first one is the psi t. So psi t is what? Z is equal to 1, that is ds rho, this is the ds rho d rho d phi az. So to understand this point, this is very important. We want to calculate this one, psi t, right? So psi t, what we required? We required a G dot ds, as we are talking about surface top one, right? So psi t we required. Okay, so G is given already. We will require the ds. Ds is what? This is the element on this surface. This is the ds. We want this. And what we have? We have the points, so lines d rho, rho d phi and the dz. This is the elements, differential elements in the cylindrical coordinate system, d rho, rho d phi and the dz. So for this particular surface, what is constant? Rho, phi or z? Obviously z. So because this is at the height of z is equal to 1. So it means z is constant, what left? D rho and rho d phi. So it means the ds will be what? So this ds will be rho d rho d phi. So we can take this one as, we have to raise this so that things must be clear to all of you. We want ds. I will take the example of this ds. So in this case, ds will be what? Ds will be, z is constant, it means the dz will be 0, because there is, when z is constant, then dz will be 0 obviously. So ds will be what? This will be d rho and rho d phi. And direction of this surface will be what? This will be a z. Because as we are aware that the direction of the surface of any surface will be perpendicular to that surface. If I want the direction of this surface, so the direction of this surface will be what? Always be perpendicular to this surface. Okay. So these things must be clear to all of you in all the throughout this course. If this point is clear to all of you, it will be good for you all. ds is d rho, rho d phi and dz. So we can see here, first thing is g is given, as I said, ds is rho d phi into az. Same thing is here. I hope this point is clear to all of you. Then g is given, ds is given. Now g and ds both are given. Now the main important point is the limits for this question. Okay, so for that one, okay, you can see we have this surface. I will take this surface here outside. This is the point I am taking this one as here. So from here to here, what is the value of rho? At the center, rho is 0, and what at the extreme point, rho is 1. So this is rho is equal to 0 to rho is equal to 1. I think this point must be clear. Second, now what is the second variable? First is a rho variable. So we have taken the rho 0 to 1. Now we have the phi. Phi is variable. So it means phi is from here to here. So what is this angle? From 0 to 2 pi. Okay. So in this case, we can take rho is 0 to 1 and phi is 0 to 2 pi. So in this way, we can integrate this. First, we will integrate with in terms of rho, and then we will integrate in terms of phi. So final result for this one will be 10 pi e to the power minus 2. So this is the case for the first surface on the cylinder. Second is the phi b, right? Phi b is what? Phi b is the bottom one. So this is the line which we want to find. So we want the psi b. So this is the bottom flux lines which we have to calculate. That is g dot ds. Okay. So for this case, what we have now talk. For this one, z was 1. For this surface, z is equal to 0, because limits of z is 0 to 1. So for this surface, z is equal to 0. So when z is equal to 0, so what we have, and now we can take this surface here as well. So again, rho is equal to 0 to 1 and phi is 0 to 2 pi. Okay. So this is 0 to 1 and phi is 0 to 2 pi. Okay. But z is equal to 0. Same thing is there. ds is same. But what is the difference in the ds? In this case, in the first one, we have seen the direction of ds is outward. So there is a positive z direction. Now for this case, flux is going outside. So it means the direction of this surface will be downward. So this is your minus of az. So in this case, we can see that for phi b, z is 0 and ds is rho d phi into minus az. So simply we can write this one, and phi, so rho will be 0 to 1, phi will be 0 to 2 pi, 10 e naught rho d phi. So in this case, when you solve this one, then the result will be minus of 10 pi. So this is the case for the psi b. Now come to the psi s. So for that psi s is what? This is the surface of the cylinder. Now we want the how much flux is going out from the surface of the cylinder. First thing, we have calculated the how much flux going out from that from the topmost surface of the cylinder. Second, we have calculated the how much flux is going out from the bottom surface of the cylinder. Now third one is the we want to calculate the total flux going out from that surface. So for this case, what we have now, we will talk about this surface. This is the psi s. For psi s, what is the constant value? Variables what we have? Variable is rho phi z. So for this surface, what is constant? Rho is constant for the surface, and height is variable 0 to 1, and phi is varying from 0 to 2 pi. So for this surface, those rho is constant. So we can write it. What is the value of rho? Rho is 1. What is ds? ds is equal to what? What we have? D rho, rho d phi and ds, dz. What is this? As I said, this is the differential length, right? So rho is constant. It means the rho is constant means d rho will be 0, because the differentiation of the constant value is 0 always. So d rho is 0, right? Then we have rho d phi and dz. It means the surface area for this one will be, this is the surface area, we can take this one. So for this one is we can take as the, this value will be rho d phi into dz. This is your ds. Okay, so in this case ds is what? Rho dz d phi. I hope this point is clear. So direction of this surface will be what? Direction of this surface will be outward from the surface. So the outward direction is the rho. So in this case, that is why this value ds is equal to rho dz d phi into a rho, right? So just put all together into this equation. So rho s will be g dot ds, and here what are limits? Limits is from z is varying from 0 to 1. So this is a 0 to 1. Rho is constant value, that is equal to 1. So we can put the value of rho 1, and then this phi is varying from 0 to 2 pi, right? So this is the 0 to 2 pi. So in this case, when you put all together, because see, you have to practice the integrations, right? You must know about the integration, what are the integrations and so on. Then only you can solve this type of problems. In EMFT, this trigonometrical part is very, very important. You must know all these things. Okay, so psi t is there, psi b and the psi s, these three are there. Okay, so what we need to do, simply if you remember that our main requirement is now we have to add psi t plus psi b and psi s. So in this case, so simply add this, psi is equal to psi t plus psi b plus psi s. When you solve this, then you will get the value 0. Okay, then we can confirm this. So this confirmation will be based on the divergence theorem. Apply this divergence theorem, that is equal to g dot ds is equal to del dot g into dv. So what you need to do, because we have taken this value, so this value which we are getting, that is 0. Now just we have to solve this del dot d. So first take the divergence of this. So this is the formula for the divergence of in the cylindrical coordinate system, that is 1 upon rho del rho rho d rho plus 1 upon rho del phi g phi plus del z dz. So simply put the values of g rho and the g phi and gz, then you will get the same result, that is 0. But this doesn't mean that this 0 when you are taking this one as a 0, first you have to take the divergence of this value del dot g. If it is 0, then it automatically we can say the flux is del dot d g is into dv is equal to 0. So in this case, we can see that the flux passing through the surface, through the closed surface, is equal to the divergence of the volume integral of that surface. Okay, so till so that is why we can solve this type of problems. Any kind of problem we can solve it when we want to find the flux lines, or we have to prove the divergence theorem. In the next lecture, we will continue from here, that is the curl of the vectors. So we will take the one of the example from there and it will help you to understand. Thank you very much.